Okay, hi everyone. So this is the last part of your atomic absorption spectroscopy lecture. So I would like to continue on the different types of atomic absorption spectroscopy. So before this, you have learned about flame atomic absorption spectroscopy and how would everything be apa? The sample being aspirated, atomized, and then you have learned about graphite furnace, where it has a much more less sample preparation because your sample just need to put it onto the graphite furnace, and then straight away the atomization process would happen inside the graphite furnace. All right, so that is the difference in terms of flame AAS and GF AAS. So you need to be able to know the difference between those two. So as shown in this slide, the difference is that, for example, graphite furnace, you need much more smaller sample size as compared to flame. The detection limit for graphite furnace is at ppb part per billion, while for flame it is at ppm. And then in terms of residence time, uh, longer analysis will be needed for graphite furnace as compared to flame. It is as I mentioned, the sample preparation is minimized for graphite furnace. Longer residence time. Residence time here means that the time spent for the sample to be inside the graphite or inside the flame. So in terms of the graphite furnace, it needs much more longer residence time. Therefore, longer residence times will enhance the sensitivity as compared to flame. We have only short residence time. Okay, so let's move on to the another special. I would say that very specific AAS, which is called hydride generation atomic absorption spectroscopy. All right. So in this case, it is following APA 3114. APA is an organization where it have the standard methods. Okay. So basically, why hydride generation AAS is special, because certain metalloid elements will be able to form covalent hydrides, volatile covalent hydrides, which can be separated from the main matrix. So now you imagine that your analyte, which is in this case your metal, is in the sample. Sample have a lot of matrices inside the sample, so you need to be able to just select your analyte, which is your metal, out from the matrices, and then you do your analysis, which will enhance its sensitivity. Okay, because we don't have the matrix interferences anymore. So there are certain metalloids that can form volatile covalent hydrides. Means that your analyte, your metal is volatile when it is in a hydride form. Therefore, when it is volatile, which is much more easier for us to separate it from the main matrix. So this is a standard method for hydride generation, where it uses sodium borohydride as shown inside this equation. So sodium borohydride will added with water and sodium chloride. So you would get this, which is the metal hydride form in a gaseous form. Okay, so the hydride is then decomposed in a heated quartz tube through which the spectrometer radiation passes. So when we have mix the sodium borohydride with your metal, it form a metal hydride. Then the hydride will move on onto the quartz tube, where it decomposes to become atom. Where at this place in the quartz tube, there will be the radiation comes in. Okay, so the radiation is not from the beginning as what you have looked into flame AAS where you have a light source in front. Okay, so in this case, the light source would just go inside the quartz tube, where in the quartz tube itself is your hydride metal, not the matrix anymore, because the matrix we have um, dispose it beforehand. Okay, so um, so basically, for hydride generation, elements that can be analyzed belongs to group 14 and 15, 14, 15, and 16. Okay, so these are the elements or the metals that can be analyzed by hydride generation, AAS. Okay, so there is another one which is much more specific. It is just for the determination of mercury in environmental sample. So this is basically uh, APA 3112B, which is called cold vapor AAS method. Need to remind you here that this is very important, the keyword of cold vapor. So cold vapor, you straight away think that it's for determination of mercury. Okay. All right. Mercury has an appreciable vapor pressure at room temperature. So mercury itself, when it is in at room temperature, it is availably volatile. Okay, so that's why, for example, when you learn about the laboratory safety and health, uh, for example, when you broke a thermometer, you need to straight away, have some precautionary measures, because mercury is volatile. So it may affect you if you have not have precautionary measures. All right. So therefore, when it is means that it is volatile at room temperature, so the element is generated by chemical reduction. No other atomization is required. All right. So the mercury is usually reduced by the reaction with tin 2 chloride. All right. So the mercury vapor is then carried into the light path in a stream of air or noble gas. So basically, uh, mercury also will be available for hydride generation, but we don't need it to be apa uh, don't need to combine with sodium borohydride, because it is volatile enough to be to be analyzed. So that's why we have here cold vapor. So means that cold vapor, the AS method, it is being conducted in a low temperature. Okay, so that the volatility will be minimized. All right, so this is the hydride generation AAS. So this is an example of the instrument. Okay, so basically the schematic diagram of this special hydride generation AAS looks like this. Okay, so uh, here is your HCl, here is your sodium borohydride, where it will be mixed with your sample. Okay, with your sample, and then it is being separated into the quartz tube. Okay, the quartz tube afterhand, and then it will be atomized. Okay, so this is the the initial part of it. Okay, so HCl flows here, sodium borohydride flows here, where it will be mixed in this mixing section, mixed with your sample. Okay, all right. So basically, this is for the analysis. I mean that the procedure. So prior to analysis, the aqueous or solid sample must be prepared according to the procedure APA 3112. For hydride generation is 3114. Sorry, for cold vapor is 3112B. Okay. So basically, this is how the films would work lah. So you will be able to read throughout this procedure. Okay. All right. So the advantages and the limitations of hydride generation. So the advantages, it is very specific towards these metals. So if there is a question in terms of we do have this metal and it is um, it is in our water sample, so we want to analyze this kind of metals. So if you have seen this kind of metals, AS, SI, GE, PB, SB, SE, SN, and TE, which is at group 14, 15, and 16. So this, you straight away just go to hydride generation. Don't ever think of going into flame AS ke, GF AAS ke, because it is very special towards hydride generation. Okay, because the detection limit is well below the ppm range are achievable. The extremely low detection limits results from a much higher sampling efficiency. Okay, so I think it would be much more better if all of you, this is not a homework, but this is something that will be beneficial for you to come out with a table where it comprised of the sample that needed to be analyzed. So which instruments do you think that is good enough? So for all of this for all of these metals, straight away hydride generation. For cold vapor, straight away to Hg, mercury. So you don't when you come up with that table, you don't need to you don't need to think much, because you have segregated them according to the instrument that is beneficial for each of the analyte that you are going to be analyzed. Okay? So the limitations is that, okay, the limitation of hydride generation, it is limited for these metals only lah, these elements. So it may be a limitation, but it also can act as an advantages. Okay, so the limitation is that the formation of the analyte hydrides is suppressed by a number of common matrix components, leaving the technique subject to chemical interferences. All right, so you have, even though you have be able to generate a metal hydride, which is volatile enough, but there may be some some components in your matrix also. Maybe for example, you want to analyze AS only. You want to analyze AS only, but for some reason there are some SI inside it as well. So SI here would be counted as interferences because your compound of interest or your analyte is AS. So SI would act as a chemical interferences later on. That is the limitation, because it's quite apa? It's quite large number of some of elements that can be detected by hydride generation. Okay. All right. So let's look on the cold vapor. So the cold vapor, the advantages is that improved sensitivity with 100% sampling efficiency. So all of the Hg in a sample solution is placed in a reaction flask, is chemically atomized and transported onto the sample cell for measurement. So the detection limit is approximately 0.02 ppm. Okay. So the disadvantages pula, we can look at cold vapor is very limited to Hg only. You can look at as a advantages, but you also can look at as a disadvantages. So because when you say that it only can detect apa? It only can detect mercury, it can act as a very specific, or it can act as a disadvantages. Okay. No other elements offer the possible of chemical reduction to a volatile free atomic state at room temperature. So that's why it is very limited to mercury only. All right. So it's imposed by background or contamination levels of Hg in the reagent or system hardware. This may be one of the disadvantages where it comes from the instrument itself. All right. So yes, so the monochromator is something that you have learned before. So it still serves the same purposes, where it just select the wavelength that you want. The function of the monochromator is that when you have done your when you, even though for example in flame AAS, even though you have selected the particular wavelength, just one wavelength, because in your hollow cathode lamp, there is an element which is the same element as what you want to analyze in your uh, in your sample. So if you want to analyze copper in the HCl, you should have copper metal. In your sample also, you want to have a copper metal, because only copper metal can generate a wavelength that is going to excite the copper metal or copper analyte inside your sample. So the function of the monochromator after the sample has been excited, because you want to be able to select again just copper wavelength, which will be recorded by your detector. Because during the excitation inside the flame, even though there is just copper that will be excited, there may be some other components inside there which will be able to be excited, because it have the same wavelength. So this kind of excitation might be might be releases some kind of other electromagnetic radiation wavelength. So the function of the monochromator is to select back your only wavelength for your copper. So that's why the monochromator is being after the sample, after the flame lah. Okay. So the photomultiplier tube is the detector that you have learned before. So the function is still the same, the process is still the same. Okay. So these are the application of AAS. So the you can see here there is a lot of standard methods corresponds to atomic absorption spectroscopy. So you may take a look into it later on. So basically, in summary, uh, you can see. I think this figure says out a lot lah. So for AA, for atomic absorption, the light source must be here, and you have flame AAS, GFAS, or cold vapor or hydride atomic absorption. Then you would have your monochromator. Then you have your detector. ICP or ICP-MS you will learn in the next chapter. But for ICP, there is just a plasma here, okay, plasma, where the plasma, this is your atomizer, this is also your source of light, where the emission will be detected by that detected by a detector, but there is a monochromator here as well. Okay, so basically, if as I mentioned before, if you can straight away make a table. Okay, flame AAS. So what is the residence time? What is the compound that can be analyzed by flame AAS? What is about the sensitivity? What is the detection limit? So when you have those complete apa those complete properties of each of the instruments in terms of absorption spectroscopy, then that is basically your chapter 3, basically. So this is how I learned before. Okay, so I think it's going to be beneficial for you. All right. All right. So as before, when we have learned for UV visible, so there are interferences also that's going to be happening inside your analysis. So interferences and control measures, the interferences can comes from two division, which is non-spectral interferences and spectral interferences. So basically for spectral interferences, it's just about the background absorption. Okay, the continuum source from the background correction, and also Zeeman background correction. So for the spectral, uh, I think that, okay, let me see here. Okay, so spectral interferences, okay, due to the radiation overlapping that of the light source. The interference radiation may be an emission line from another element or compound, or general background radiation from the flame, solvent, or analytical sample. So the correction is that we need to use alternative wavelength. For example, copper at 710 nanometer. All right. So for these ones, let me see. All right, spectral interferences comes from the radiation that is overlapping. Means that your light sources also have some radiation comes from it. Okay, so I think we can look at this one. Yes, background correction, particularly important in graphite furnace AS. So do you still remember that we have a beam chopper here? Okay, so I want you to imagine that you have your radiation, I mean that your particular wavelength comes from the lamp, and there is also a radiation comes from the flame itself. So this radiation is the same because the radiate. Okay, let me put copper straight away. Copper. So from the lamp you have a copper radiation. From the sample also you will have a copper uh, a radiation which will be detected by the apa the detector. So when this chopper is at this position, your detector would be able to detect both radiation from the lamp and also from the flame. So you have much more higher reading because both radiations serves for copper wavelength. But when it is in this position, the radiation from your lamp is being blocked. But only radiation comes from the burner or from the flame, which is your sample radiation. So that's why in terms of the resulting signal later on, you have some kind of this signal where the top part here would comes from your lamp and flame. While at the bottom part here, this is just comes from your flame. This is what we want. So we'll be able to detect both radiation and one radiation. We just subtract it. So it will create a results based on the flame only. Okay. I hope that explain in terms of spectral interferences. All right. All right. So this is due to the overlapping. That's what I've explained. So that's why we have a chopper. So interferences also may comes from may comes from a radiation which is another element inside the matrix itself, the one that I've mentioned before. Okay, so that there is an example of other spectral interferences lah. All right. So for matrix interferences, this is due to the differences between of the surface tension, the viscosity of the test solution, and the standard. So the correction is that we need to do a matrix match of all the samples and standards and the blanks as well. So, and the third one is the chemical interferences. So this one is that because we do want certain components that are thermally stable will not be able to decompose with the typical energy which is in the flame. So maybe some elements would be able to withstand the flame temperature which lead to non-atomization. So the correction is that we need to have a releasing agent to free the atoms to be produced in the flame, and also maybe add another complexing agent in terms of the EDTA, which can reduce the the thermally stable components into a thermally unstable component so that it can be atomized. Okay. All right, so ionization interferences, as I mentioned before, we don't want your atom to be atomized because atomization is non-desirable. So the temperature of the flame is too hot enough to excite the atoms beyond the ground state to remove electrons, therefore creating ions. So we don't want this. If we don't want this to happen because in the atomization process, there is also a chance for it to be ionized. So how are we going to do this? Is that we easily add an easily ionizable element, means that 0.5% potassium. So when we add potassium, which is easily ionized element, it will create a surplus of electrons inside the solution. Therefore, the equilibrium will shift towards the production of ground state atom because there is too much of K plus inside it. So the ionization will be hindered, the ionization process lah. So that's why it will just stay, your metal or your compound of interest will be just until atomization. All right, so I think that's the end of our atomic absorption spectroscopy. So thank you again all. All right.